Yeah, so what I'm gonna run through is some of our traditional problems with SQL Server. I mean, I would say 19 out of 10 times that I come to a site with a SQL Server performance problem, it's storage related. So I'm gonna go really deep into storage. Why we need to fix this. Well, then we're gonna look at old technology in the marketplace, but new technology for Windows. We're gonna look at the SMB protocol, you know, file shares. And we're gonna look a little bit on how we can design new SQL Server platforms based on Windows Server 2012 and SQL Server 2012. My background is I've been working with Windows since NT 3.1 back in 1993. I was 1 out of 3 beta testers in Denmark. I was working at the largest OEM back then. We were larger than HP, Compaq and IBM together. And through that relationship, I started working in Redmond as a consultant to the product groups. I started working with SQL Server since version 4.21a, which was the first one Microsoft did by themselves. And I've been working with the SQL Server product team on various consulting and R&D stuff since SQL Server 7. Currently, I'm working on SQL Server vNext, so the next version of SQL, whether that be SQL 2014, 2015, or R2, I don't know. But I'm involved in speccing what the next release will be doing. On the Windows side, I spent the last 2 years on Windows 8 kernels development, or Windows Server 2012, mainly on storage-related issues and on Hyper-V. It turns out that the SQL Server team doesn't understand virtualization and the Hyper-V team doesn't understand SQL Server. So I was hired by the SQL Server team to basically be their arm inside of the Hyper-V team and educate them on if we want to build a hypervisor that can virtualize large SQL Server workloads, what does a hypervisor need to support in order for that to be successful? Over the years, I've done a lot of reference cases when Gartner moved SQL Server into the leaders quadrant of the Magic Quadrant. They mentioned 3 customers, and 2 of those were my customers, and the last one was an American bank based on guidelines I helped work out with HP in the US. So basically, HP has a team of 5 people inside of Redmond, where these 5 engineers have full source code access to both SQL Server and Windows. So whenever Microsoft do a new build, HP's engineers run it, they see a problem, they actually take the source, fix it, and check that back into Microsoft and say, hey Microsoft, could you please fix there's a bug in your code, it doesn't run fast. And that team does all the Windows guidelines and SQL Server guidelines, and I've been working with those guys since 2003-04. And I'm a little into motorsport, so I got this kitsch thing from HP, Intel, and Microsoft for actually doing some of these reference cases. And that's what I've been doing for a lot of years. Enough of me. So, storage challenges. I mean, traditionally we have various kinds of, yeah?
Who are you hired by? I mean, I always like to know, you're not working for, you're not employed by Microsoft?
No.
Are you independent?
Yeah, independent. Okay. So since June last year, I started my own company. I've started 2 different companies, and now I got tired of having employees, and so being a corporation of 1 means.
Well, that's like mine. Okay.
Yeah, and it's mental note.
But still, you're not independent. But that's not the case. You're dependent on your customer. Yeah.
Well, I'm based on Microsoft technology, but I work with all the hardware vendors. The reason I work with HP R&D in Fort Collins and in Palo Alto and in Houston is HP, I think, makes really good products, but also they have the broadest product line. And once you know a PCI Express 3.0 bus from one vendor, it's the same on the others. But if Klaus closes his ears, I have customers that work with Dell, IBM, whatever, but my personal favorite, and I can also back that up technically, is HP. So going back to the agenda. So storage problems. I mean, we used to have capacity problems. That's not an issue anymore. Drives are big, whether it's mechanical or solid state or NAND flash. Then we have fast. I mean, we can do fast storage, but usually it's direct attached. But whenever we need a SQL Server instance that needs fast storage, it's usually important for the company. So we cluster it. But when we cluster it, we need shared storage. And shared storage usually means traditional storage arrays, and storage arrays and fast is usually not what we put in the same sentence. So we need to have a way of fixing this. Then we need the shared storage for the clustering. We can do that, and then we need reliability. And I'm gonna go back to why I don't think the current setup of clustering and doing SQL Server high available setups is not as reliable as we want it to be. So speaking to storage vendors, it's usually if you spend more money, storage will be faster. The reality usually is, even though you spend more money, it flattens out. Nothing happens. And even worse, we actually see whenever the storage array is a non-match for SQL Server, it actually gets slower. And the reason for that is, probably all of you know that SQL Server spends a lot of CPU time converting random I/O to sequential I/O. Nobody else in the database business does it. Oracle doesn't, or DB2 doesn't. And whenever we talk the really big arrays from the traditional storage vendors, they optimize it for the big, in quotes, databases. That's usually Oracle on a mainframe, or DB2 on a mainframe, or Unix or something like that. So they optimize the storage arrays for random I/O. But when you put SQL Server on top of a storage array with a random I/O optimization, you get a sequential pattern and a random algorithm, and that usually mixes up the I/O stream, and so the performance drops. So just buying the most expensive array when it's SQL Server is usually a bad idea. For DB2, for Oracle, it's usually a good idea. The next problem with storage arrays is that even though we might have a pretty good bandwidth out of the storage array, we usually connect lots of hosts, so we get this kind of cone-shaped thing that we can put in more requests than we can actually put out the bottom. So we have a skew of how much do we request from the storage array and to how much we can actually deliver. We need the pipe to the storage arrays to go much bigger than they are today. Then we have a problem about, so we want to offload storage as much as possible. But one thing that happened with SQL Server 2005 was that Microsoft changed a lot of the algorithms. So stuff that previously ran in memory now runs in TempDB. But when stuff runs in TempDB, we access storage. And since it uses TempDB as memory, storage speeds in some situations means basically execution speed. So this was in 2007, I was writing a white paper to the SQL Server group about stuff I think they needed to change, specifically in a in a SQL Server cluster. What happens whenever you move a node? Well, you stop SQL Server, you move it to a different node, you start it again. But whenever you start SQL Server, it deletes either the TempDB header or creates the files if they're not there. So every time we start and stop SQL Server, we wipe out the content of the TempDB. So why on earth put it on shared storage? I mean, that's a limited resource. So we really want to have a local TempDB on all our cluster nodes. And back in 2007, I was writing this, and I think this is actually from the SQL Rally. And Mark Suse, maybe some of you have known. Do you know Thomas Kaiser? Does that ring a bell? From the SQL Cat team. He used to be my pupil in I/O. Now he's learning me a bit about the code inside of SQL since he spent 5 years there. But Thomas's boss is Mark Suse. And back then,
he's a really high boss on SQL Server.
Yeah, I think there's just one person above him in the SQL team.
So he was. I think. Look at the he was a keynote speaker 2 years ago at SQL Rally.
Yeah, that's true. But anyway, he said, I was complaining, don't do this, don't put TempDB on storage arrays. He said, no, we need the cache, we need the storage array, it's fantastic. It will pull down the moon to the earth and it will solve all problems. Especially, we need caching, so the more cache in the sand, the better. But the problem is that those big arrays are usually based on the performance of the cache. So we need very much cache, making sure that we never fill it up before we get some idle time and can start destaging the cache. But those storage arrays, when we fill up the cache entirely and we still don't have idle, well, what needs to happen is what an application requests isn't in cache. So I need to put it in cache, but before I can do that, I need to pull something out of cache, which means writing, deleting, fetching, storing, and delivering. So you see a almost flat drop in performance on traditional storage arrays whenever we hit the cache. Putting in more cache just means if it's every half hour we hit this problem, now it's maybe every hour or maybe every 2 hours. But we will hit this problem.
Just a side topic. What's your experience of running TempDB on RAM disks?
Well, I have a mantra of simple solutions. I mean, we can have complex problems, but we always need simple solutions. I tend to see we can do some really fantastic stuff with massive complexity in a solution. But the day-to-day operations tend to have a headache, it tends to have downtime, it tends to be troublesome. And as far as I know, there are no memory disk vendors out there that are supported by Microsoft officially. So you can't really go anywhere and say, well, I got this corruption and something broke and now we can't start our clustering. And Microsoft support will go, well, you did something that you're not supposed to do. So I would rather work around the problem and do it with supported products. So I never use it.
I just done benchmarking.
Yeah, for benchmarking it's fantastic. And that's really the problem. When I talk to the SQL Server product, if some of you have been to the US, there's a big chain of electronic stores called Fry's. It's the size of, I don't know, in Denmark it's Bilka, I don't know the largest grocery store out here, but really, really, really big, like factory big. And everything from transistors and to flat screen televisions and everything between. A Fry's is really close to the Microsoft campus. And these guys usually, when they come out with a white paper on benchmarking from Microsoft, you can almost figure out which aisle in Fry's they went to and which weekly offer they bought and how they set it up. And it's fantastic in a lab environment, in a little cubicle, it works super. But when we need to distribute it across 7 servers and network links and all kinds of stuff, it usually breaks. And I think maybe that's why both HP's R&D and Microsoft works with external people, because we have real world experience. So what works in a lab really doesn't work in the real world. But I think, yeah, for performance it's fantastic. For real operations I would never do it. But so anyway, just 2 days before the SQL rally, Mark Suse is a really straight American, but 2 days before he was in the Oktoberfest in Munich, and he was really drunk, and he experienced Europe from a very positive side, and he posted this picture of himself on Facebook just 2 days before. So I think this is public domain, and I mean, who can trust a guy that looks like that, right? So whatever he says, don't believe it. And we'll come back to Mark in a few slides. So the next problem about storage is that, well, the stack of components is really, really complex. Usually when we think of storage, we think of, well, we have some disk drives, we connect some of them to a LUN, RAID 5, RAID 1, RAID something, RAID nothing, and then we expose it over some connections. And whenever you go to your storage department and you say, well, we have a SQL Server problem, we are pretty confident we are waiting on storage. They say, well, our measurement tool inside of our storage array says we are only 8% loaded. So we have enough I/O. I will guess some of you have heard lines along that. But the problem is that inside of that storage array, we don't just have some LUN capabilities on the physical drives. We have SCSI controllers and backplanes, we have new ports, we have XOR engines that does parity for RAID, we have storage controllers, we have port CPUs, we have front-end ports, we have logic, we have cache lines. Maybe some of these are overloaded. And I'll show you an example of an EMC array, actually the biggest one, the Symmetrix VMAX, which is 11 racks of storage. How a SQL Server workload can completely turn that storage array bottom up. But if we measure the disk load, it's around 8%. And so they would usually say, we have enough, but it's somewhere else it's overloaded. Then we have the fabric switches, we have worldwide ID, we have zoning. And on the servers, we have ports, we have fiber channel adapters where we need to set queue depth. We have DSMs to control the storage controllers. We have MPIO algorithms. We need to make a lot of decisions. So from SQL Server back, we have so many layers that to make this balanced, to make data just stream through with no bottlenecks anywhere, is actually very, very difficult. That's why the fast track setup started appearing, to get an idea of how we do a balanced workflow through all the components from SQL Server back to the physical disk drive. The problem is that the fast track solutions are based only for data warehouse workloads, and only if you have the 3 databases they specify 2 staging and 1 ADV. If you have anything else, if you have 2 databases on it, you completely destroy the setup. So it's not good for most real-life situations. So we get bottlenecks everywhere in this stack. This is also why I'm often talking about reliability on a clustered SQL Server environment. Because if you have a clustered setup of SQL Server, you install all this stuff on every SQL node, and if something happens anywhere in this stack, the cluster man will say, I had a timeout of 1 I/O, so let me stop SQL Server, something's wrong on the node we're running, move it to the other node and start it again. And I'm guessing some of you has probably experienced clustered SQL Server instances moving nodes for no apparent reason. And that's a reliability issue that I actually have customers that started a SQL Server as a non-clustered, then it became important for the business operation, so they clustered it. Now they got more downtime on the clustered setup because of whenever something happens inside of this complex stack, it will move the SQL Server from one node to the other. And what happens? Well, we need to cancel our connections. We need to do a recovery on the transaction log, do roll forward and roll back of everything inside of it. So it might take seconds, it might take minutes, might take hours. My worst case on the customer was 27 days of moving from one cluster node to the other. And so I'd say, I don't know how many of you watches your virtual log files inside of the transaction log. And if you're running SQL Server 2008, R2, SP1 and back, and any previous release, there are some bugs that if you have too many virtual log files, recovery can take ages. I think the knowledge base says a long time, 27 days in recovery. That's a career record for me at least. So please, please, please make sure you have a low number of virtual log files. Below 100, preferably below 40.
Okay, so that is one of the things we talked about on the last meeting, the problems with virtual log files. So there's a recording on our website which describes how you can get a lot of virtual log files if you configure things wrong. And,
so that's a reason for joining the LinkedIn group and the Facebook page.
Yes, so because that's a really important issue, the virtual log files.
Yeah, so I have customers that actually declustered again because clustering gave more downtime than the physical servers, standalone servers. So looking, so normal storage vendors give you one number. We are 8%, we are 12% utilized. But if you ask them really nicely or pay them a lot of money, you can usually get a more detailed perspective. So this is the Symmetrix VMAX. Out here, the color says how hard are we loaded. 0 to 10%, up to 90 to 100% loaded. Up here, these are the ports to the storage array. These ones here are the port processors. Here we have cache lines, and down here we have the SCSI controllers, and here these are all the physical drives inside the storage array. And over here, this group is actually an NAND flash or solid state drives inside it. And this was the initial configuration. As any storage vendor, they were confident, out of the box, we are just brilliant and we will actually pull the moon down. So what we saw was, we waited on storage from SQL Server. And when we started looking inside of it, well, the storage, the spindles were not utilized, but up here, we were in the higher end of utilization. So they said, okay, we can fix this. We have a best practice for big databases, meaning Oracle and DB2. So what we got out of it was this picture. Now we are 100% utilized on the port processors and still nothing coming through. But every single storage array I have met in my career, when we get one number in utilization on a storage array, it's always on the back-end spindles, because it will be the point where we have the lowest utilization. So the storage guys would say 8% utilized. You would sit in SQL Server, say we're waiting on I/O. Who's right? But when we
saying that this picture you cannot see through the normal monitoring tools.
No. I think in HP's camp, in your big arrays, it's like 500,000 Danish you pay for the tools to do this advanced analysis. And so I would guess EMC, HDS, everyone else is probably in the same price range. So it's an expensive tool to get this view. Depending on the service contract you have with your storage vendor, maybe I sometimes see that the customer don't pay for this. You get one of the consultants from the vendor to go in and pull out these reports, because they have access to the tools.
Then you pay 5,000 per hour instead.
I will not go into that. So then we gave it another shot, saying, well, SQL Server is a little different. Maybe we can tweak it. And that's just to make that clear. I think there were some questions about that the last time I did this session. There's not one way to do it that work on all storage arrays. There's a unique way of every single storage array. Even within one vendor, it's different how we tune the storage array for SQL Server workloads. But we tuned this Symmetrix VMAX to a SQL Server pattern. And what we got was this workload, which is what we really want. Here we pulled out 12 gigabytes a second all of a sudden, where we did about 800, 900 megabytes before. But now our spindles are fully loaded. We are balanced all the way through up here and have enough capacity, and we never overload our cache lines. This is a picture we want from a SQL Server storage subsystem. And one really funny thing is that once you take modern technology like NAND flash storage and put it behind all these legacy components, well, the advantage really goes away. You can see we almost pulled the same I/O and throughput through the mechanical spindles as we did the NAND flash. But if you put a solid state drive on a laptop, you get a factor of 100 or 1,000 increase. So we need new technology to get rid of this legacy. So how do we connect to storage? Well, I guess the most common thing is fiber channel. But fiber channel has been stuck at 8 gigabit a second for ages. We do have 16 gigabit, but it's the very few vendors that does 16 gigabit. It's hideously expensive. It's like a factor 3, 4, 5 more expensive than 8 gigabit for just double performance. A lot of the switch fabrics doesn't support it yet, and a lot of vendors doesn't support it. So I don't know if any of you are running 16 gigabit fiber channel, but my guess would be no. I have yet to meet a customer that runs it in production. And they're even moving to FCOE or fiber channel or Ethernet. So even the fiber channel world is moving over to different interfaces. You have iSCSI. Well, iSCSI's problem was that it started as a low-cost alternative to fiber channel. So most of the iSCSI implementations are 1 gigabit. The ones that do run 10 gigabit usually don't have enough ports. So in a big array, I can do 16, 32, or 100 fiber channel interfaces. But for iSCSI, it's usually a much lower number. So although it's 10 gigabit instead of 8, if I can only do 4 or 8 connections, I still don't get an improvement in performance. So that's for block level storage. That's when the servers see the disks presented from a storage array as a local. Then we have network attached storage, where we use it as a file share. But I'm guessing most of you have tried over the years to copy a file from one server to another over the network, and somewhere in the middle, all of a sudden it says network name no longer exists. So, I mean, who would in the right mind put transaction logs of your mission critical SQL servers on a file share? I wouldn't, personally. And while looking for screenshots that exemplifies this, it turns out that that kind of problem is not just a Windows issue. It exists on platforms that have no faults, apparently. But maybe there's a reason why this has so many problems. This is some of the command set from the SMB protocol. So if you think about it, how much can you do to a file share? I can create a file, I can delete a file, I can modify it, I can modify its attributes, I can set rights. I mean, I can do very few things. A command set with 100+ commands to manipulate things. I mean, just writing, there are 14 different write commands in the SMB protocol. As a developer, which one would I choose? So to me, it makes perfect sense why you have instabilities on SMB. So Microsoft took to it to clean it up. So the next version, they cleaned it up, 19 commands, one write, one read, and so on. And the requirement was TCP, but I'm guessing none of you runs any of these anymore. The next thing they did on the 2.1 version, saying, well, so its stability is getting better, but we need to get some throughput. So I don't know if you know MTU sizes or jumbo frames, but normally we send 1500 bytes in every packet. And jumbo frames, we can go to 9,000 bytes on a packet. That's a call, so the term is an MTU size. So what Microsoft did was support sizes up to 1 megabytes, so that the overhead of the TCP encoding would be really, really low. The one problem was that it wasn't enabled by default, so you needed to manually go in and hack the registry to actually get this feature. So most that did try to use it still got low performance on 2008 R2 because it wasn't enabled. The next thing was that when you copy a file from one node to another over the network, maybe you have gigabit networking, you think we should be able to pull 100 megabytes a second, but you see it going along 20, 23 megabytes per second, and thinking, what the heck is going on? I have solid state on that one, I have solid state on that one, I have gigabit Ethernet, and nothing happens. And it doesn't utilize the bandwidth. That's because by default, TCP/IP stack in Windows doesn't open more channels whenever it needs more data. So it'll just be one thread going through with one I/O in the queue, and that just takes so long that you can't really utilize the bandwidth. So what happened in the Win 7 kernel was that now they supported multiple channels, but whatever used it needed to manually implement it in every single tool. Somewhat like the 3GB switch and the AWE, if some of you remember SQL Server on 32-bit, where we wanted to access more than 4 GB of memory, we need to hard code the applications to utilize this. And it was the same on this. Robocopy, for example, is a good example. Maybe some of you used Robocopy, manually started many instances. On 2008 R2, it's just a switch on the command line saying, I want to run 8 threads, 12 threads, or something like that. But manually, and every tool needed to implement it. Seen from a SQL Server perspective, well, before 2008, it wasn't supported to use file shares as storage. You could enable it with a trace flag, but you were on your own. In 2008 R2, it was officially supported. You didn't need to use the trace flag, but you couldn't use it as storage for clustering, and you couldn't use it for system databases. So two things happened. Well, SQL Server was released, I think, in April last year, and Windows Server was in September. But they included some support in 2012 when they released it that actually made no sense until we got Windows 2012. And some of that support is that, well, we get expanded UNC support, so now we can place everything on a file share, system databases, and we can now use a file share as shared storage. So I can build a SQL Server cluster with no SAN connectivity, with no shared components, and on all my SQL nodes, I'll just point to whack server name, whack share name as my shared storage component. And I'll get back to why that is interesting. And finally, officially, TempDB can now be put in local storage. So if you configure a path, let's say d:\tempdb on all your nodes in the cluster, SQL Server can now have TempDB reside on non-shared storage or not on the file shares. So for example, you can buy a Fusion IO card, which is really good at all these small accesses that you do in TempDB, and put it locally. So we offload our shared storage for the TempDB activity. And then I met Mark back in November on the staircase, and he stopped me and said, by the way, great suggestion with TempDB. So it's really funny that I still have his 5-year-old emails. It just took 5 years to make them realize it. We can actually do this on 2008 R2. It's in the code. It's not supported, and I'm not supposed to tell how you do it, and I wouldn't do it. Just upgrade and it is fully supported. So Windows 2012 brought some new things to the table. First of all, InfiniBand. Any of you running InfiniBand for anything? Maybe high performance clusters or supercomputing calculations? No. I'll get really deep into what InfiniBand is and why it's good for SQL Server. But it's an old technology, but it's new that Windows support it. The next thing is that teaming. So I'm guessing that on your high-end servers you probably have more than one NIC and you team them. So if one falls out, you'll still have connectivity, or maybe you team them for performance reasons to get more throughput to your SQL servers. But the problem is it was never supported by Microsoft. They didn't have an API to do teamed NICs that are virtual based on physical implementations. So some vendors, if you're HP, I consider you lucky, because they write their own teaming software that will support whatever NICs they sell. So if you have Broadcom, Intel, Emulex inside of the same system, it's still just one virtual NIC driver. If you're IBM customer, well, IBM didn't do that. So you might have Broadcom NICs on board, you have Intel NICs for your cluster communication, and you have, let's say, Emulex for your LAN connectivity. Then you need to install 3 different NIC teaming softwares on the same server, which also usually creates problems. And Microsoft has in many situations said, well, for this particular area we are not supporting teamed NICs. Finally, they grew up, they got rid of all this, and now it's part of the OS. So no NIC vendor, no hardware vendor, no anything needs to do this. Whatever NIC is in there, Microsoft now takes care of teaming. But for this scenario particularly, we don't need it so much anymore, except for very special reasons. But the important thing is they cleaned up the entire networking stack. And then they came out with a new version of SMB called 3.0. You saw the previous one was 2.1. In all the development of Windows 8, it was called version 2.2 plus. But I think somewhere in the line, at the marketing department looked at the SMB 2.2 plus as not as big a leap as maybe 3.0. So I think just very, very few weeks before release, it was bumped from 2.2 plus to 3.0. But it brings a lot of interesting stuff with it, and I'll get into that in a moment. So going back to InfiniBand. Well, InfiniBand has many characteristics, but the ones we want for SQL Server installation is massive throughput. We really need to load our CPUs, and just saying current generation Intel Xeons, they will scan at about 700 to 900 megabytes a second per core. So if you look at how many cores in a modern server you have, multiply that by, let's say, 800 megabytes a second, you get a very high number. If you want your CPUs to be utilized, you need a storage array that can deliver many, many gigabytes a second. Next thing is RDMA. I'll get into RDMA, but so you know DMA, direct memory access, where an application can access the memory space of an add-in card in a system. That bypasses a lot of checks and makes I/O really fast. RDMA stands for remote DMA, where basically, let's say SQL Server on one server can access the memory space of an add-in card in a second server. And if we do that, we need the next thing, namely low latency. If we want to access something remote, we still need it to be as fast as if it was placed locally. And that's where InfiniBand comes in. It has massive throughput, it's RDMA capable, and it has low latency. So to achieve throughput, well, we have high-speed internet. I mean, some of you are probably, most of you are running 10 gigabit. Some of you might be running 40 gigabit. And we also do have actually 100 gigabit Ethernet standard. But currently it's only for switch-to-switch communication. I know of no NICs that run at 40 gigabit. Sorry, 100 gigabit. But you can do 40 gigabit. But I'm guessing no one in here does it. It's still expensive, it's still proprietary, and the switches are not really available. they tried to do a lot in the Ethernet space to make it grow up. But even though we are at 40 gigabit, the actual speed we do is 10 gigabit. And that's starting to get really old. InfiniBand today is running, depending on who you talk to, the correct number is 54.6 gigabit per second. Some places it's rounded down to 54. Some places like storage vendors it's rounded up to 56 gigabit per second. So 50 something between 54 and 56 gigabit per second is what InfiniBand runs at. If you compare that to fiber channel, 8 gigabit, compared to Ethernet, 10 gigabit, InfiniBand is massively faster. And the way it's implemented is like PCI slots. So you probably know that a PCI slot can be an X1, an X4, an X8, an X16. So you put graphics card in X16, you put rate controller in X8 and so on. That's because we do multiple lanes of traffic. So the normal one you run on InfiniBand is 4 lanes in parallel. And the name of the InfiniBand technology depends on how fast is one lane. So the current generation runs 14 gigabit in 4 lanes. So that's called FDR, 14 data rate. And that gives us our 56 gigabit per second. Then the next thing is that you probably know that most technologies run 8 10-bit encoding. So I send 10 bits, but out of those 10 I only get 8 because I have a control bit in the start and a control bit in the end. That means 20% is lost in management. So the current generation of InfiniBand runs 66, 64-bit encoding. So out of 66 bits, only 2 are lost. So it's very, very low overhead we have on the protocol. And that actually means on every single port, we can do 6.8 gigabyte a second. That gives us a new problem, because the current generation of servers that most have deployed are Gen 2 PCI, and a PCI Gen 2 8X slot actually only moves 3 gigabytes a second. But just imagine that your storage bottlenecks for your SQL servers are now being moved to the maximum bandwidth of your PCI slots. I mean, that's a happy situation because we can do something about that. We either get newer servers with Gen 3, which has the capability, or we can use more cards in multiple PCI slots to get the bandwidth. But it's no longer our interconnect that actually have the bandwidth bottleneck. The next thing is how fast can we utilize the bandwidth? So looking at the packet size, well, we know that normal Ethernet MTU size is 1500 bytes. That's around here. So this line here, this is traditional Ethernet. And this is the bandwidth we can get through. So with traditionally configured with no jumbo frames or anything, we really don't get a good throughput. We need to go like Microsoft supported but not enabled, like 1 megabyte sizes in order to get the bandwidth that the interface can actually move. Whereas if we look at this line here, this is InfiniBand with very, very small packet sizes. And if you just move to the 1500, we are actually at almost full bandwidth immediately because of how it's implemented. But there's something in between to make it really confusing, and that's Rocky. RDMA or converged Ethernet. Intel has produced 1 NIC with one specific chip, and Mellanox has produced 1 NIC with one specific chip, where you can run this RDMA that's normally an InfiniBand technology, but you can run it on Ethernet. And once we run RDMA on Ethernet, you see that we get some of the performance that we get on InfiniBand. Because for some, getting InfiniBand infrastructure might be a problem, having a new set of switch fabrics and a new set of NICs and so on. But so we can do something. Cost-wise, switch prices tend to be from half of 10 gigabit Ethernet to double of 10 gigabit Ethernet, depending on which switch vendor you use. The networking cards, for example, for Mellanox, it's the same. So the same card can run 10 gigabit Ethernet, 40 gigabit Ethernet, and InfiniBand FDR 56 gigabit. And you choose what each port runs. But the reason it's fast when we run RDMA is that whenever we get something that wants to talk over the network, the socket direct protocol, or it's actually called SMB direct inside of Windows 2012 or the Win8 kernel, snaps it up and says, hey, we're talking over a NIC that does RDMA. So let's bypass the Windows kernel, let's bypass the TCP/IP stack, the drivers and everything, and we can actually just run around it and talk directly to the hardware down here. That's pretty interesting. The reason we can do that is also because the NICs need to have special firmware and everything to be supported for RDMA. But because that's an industry-wide standard and it's normal in InfiniBand, well, Microsoft didn't have to make the vendors do anything special. And this is really fast. I just skipped this because it just goes through traditional bottlenecks in normal Ethernet. And something has happened. So the Ethernet world tried to say, well, what if we interrupt coalesce? Instead of throwing interrupts every time we need to do a little packet, let's wait maybe 50 microseconds and collect all the interrupts and then burst them in one interrupt. That's good for bandwidth, but since we wait, it's bad for latency. Then jumbo frames, where we can do larger packets. As you saw on the bandwidth graphs, we really need large packets to do big workloads. But the problem with jumbo frames is that every single component from the client to the server needs to support jumbo frames. So the switches, all links, routers, everything need to be configured and set up for jumbo frames. If just one spot on that string isn't jumbo frames enabled, well, it won't work. Hardware checksum. Well, you have probably seen, no, I'll get back to that. Hardware checksum will really not, I mean, in benchmark testing, there was no effect. So offloading, where we can actually take the PCI stack, TCP/IP stack, and load it down to the networking card. So instead of the host processor is doing the TCP/IP traffic, the networking card does it. But I think over the years you have probably have problems with it and disabled it. And again, it hasn't shown any big improvement in performance. So they tried a lot to repair the Ethernet standard, but it never really impacted the real-life scenarios. The InfiniBand world instead, I mean, the entire stack is in silicon. Nothing runs in software. And like Mellanox, for every port, they actually have a completely processor on the card to handle it. So it's massive increase in performance.
So I think we should just find a suitable time for some coffee and refreshments.
Yeah, I think, yeah, just 2 slides and...
Yeah, 2 slides and then...
Yeah. Just quickly about the latency. If we look at the fastest 10 gigabit Ethernet NICs that are out there, we switch packets between 1 and 5 microseconds. The fastest switch out there is from Extreme Networks. It does 2.3 microsecond switching. That ends up with, even with Rocky, you know, RDMA over Ethernet, we are still looking at above 3 microseconds end-to-end communication. Looking at InfiniBand, we are in 0.1 microseconds. That's up to 50 times faster or lower latency than on Ethernet. And end-to-end is below 1 microsecond from one server initiates a packet that ends up at the other end. And this is important if we want to start using add-in cards or stuff in remote servers as if it was local. We need to be in the below 1 microsecond space. The problem has been with InfiniBand. They started life with cables or connectors called CX4. The cables were thick like this, and you could almost not bend them, and they were maximum 15 meters. So running InfiniBand between 2 server rooms, for example, wasn't really an option, so nobody used it. So we need a way to convert electricity to light and then back again to electricity. And we start thinking, but that must increase latency because we do conversion 2 times. But Intel bought a company, I don't remember that they're called, that does 550 picoseconds. And for those that haven't looked up picoseconds, I needed to do that. We're talking a lot of zeros on those microseconds, so it's really, really fast and doesn't introduce any measurable latency. So this is probably the first part of the presentation where now finally you have an interconnect that's extremely fast. We have extreme low latency, same low latency as memory access locally, and we have massive bandwidth. Yeah.
Do you think that there will come like a built-in support when you buy servers for this? I mean, today when you're buying servers, you're getting NIC cards like from HP or
yeah, it's already happening. You can do that today.
So like a standard server from HP, this comes built-in. You don't have to buy anything extra?
What HP did, what every server vendor did, was use the cheapest NICs on board to make servers retail price low. And unfortunately, everyone chose Broadcom. Broadcom is basically the same as manually introducing a problem to your servers. So I would say disable onboard NICs, put something in a slot and work with that. And because everyone did that, HP I think was the first one to do it. I think Dell today has the same option, where the onboard NICs are no longer onboard. It's a special slot. In HP it's a LUM, a flexible LUM, I think, LOM, where you actually choose yourself. My onboard NICs on this particular server should be Broadcom, Intel, Emulex, Mellanox, whatever you want. And some of those options, if you choose Mellanox, for example, you can do actually InfiniBand onboard NICs or 40 gigabit onboard NICs with these flexible LUMs. So you can basically say my onboard NIC on my server is whatever you want.
Is it more expensive or is it not the same?
I think Broadcom is the cheaper one, so it's just the price difference. But it's of course cheaper than getting a server with Broadcom on board, disabling those, and buying a whole extra NIC. Now you basically just pay for the difference. So now it's finally the customer's choice. And in HP, it's all the Gen 8 servers has this flexible LUM on board.